I'm comparing how Bayesian ridge regression handles multicollinearity, which is when several features in your dataset are highly correlated. We'll see how it stacks up against ordinary least squares, OLS, regression. I'm looking at a problem where I'm using scikit-learn's Bayesian ridge for regression, and my data has multicollinearity. Some features are strongly related. I want to understand how this affects the model's performance and its coefficient estimations. I'm evaluating several statements to determine which ones accurately describe how Bayesian ridge deals with highly correlated features in the dataset. This is like a multiple-choice question, testing your understanding. This statement says Bayesian ridge will likely give unreliable coefficient estimates due to high correlation between features. I'll determine if this is true or false. This suggests Bayesian ridge is superior to OLS in managing multicollinearity. I'll evaluate if that's a correct assessment of its capability. This statement claims that the prediction accuracy of Bayesian ridge suffers greatly from multicollinearity. I need to verify if this is an accurate description. This option proposes that Bayesian ridge automatically identifies and eliminates correlated features. I need to determine if Bayesian ridge has this built-in feature selection capability. I'm focusing on the Bayesian approach used by Bayesian ridge. It uses probability to estimate model parameters by combining prior belief about parameters with observed data. I'm highlighting the importance of prior information in a Bayesian method. It's like having some initial guess about the parameters, and this information guides the parameter estimations and reduces the impact of multicollinearity. I'm discussing regularization, a technique that helps prevent overfitting by constraining the model's coefficients. Bayesian ridge uses regularization implicitly through its Bayesian formulation. I'm explaining coefficient shrinkage. The Bayesian method shrinks the coefficients towards zero, reducing their variability and making them more stable, even with correlated features. I'm discussing OLS, ordinary least squares, regression, a common statistical method for linear regression that's highly sensitive to multicollinearity. I'm discussing what happens with OLS regression when faced with multicollinearity. It produces unstable coefficient estimations. Small data changes lead to drastic changes in coefficient values. I'm looking at a situation where some features in my dataset are highly correlated, meaning they're essentially saying the same thing. This is called multicollinearity, and it's something I need to consider when using statistical models. These are the possible answers to the quiz question about how Bayesian ridge regression handles this multicollinearity. Let's examine them one by one to see which is correct. The core of this question is about understanding how Bayesian ridge regression behaves when there is multicollinearity. Bayesian ridge regression is a specific type of regression analysis that uses Bayesian statistics. It's a pretty cool approach that helps us handle these problematic situations better than ordinary techniques. I'm testing your understanding of Bayesian ridge regression and how it behaves when features in your data are highly correlated. This is a common problem in regression. This statement is false. Although some instability might show up with extreme multicollinearity, Bayesian ridge regression is much more stable than ordinary least squares, OLS, regression. The Bayesian approach helps mitigate the effects of correlated features. This is absolutely true. That's the main advantage of Bayesian ridge regression. The Bayesian approach uses prior information to regularize the model. Basically, it shrinks the coefficients towards zero. This makes the model less sensitive to the instability caused by multicollinearity. Incorrect. While the performance might decrease, it won't be severely affected. Compared to OLS regression, Bayesian ridge handles multicollinearity better, so the negative impact on predictions is generally smaller. Nope. Bayesian ridge doesn't automatically remove features. It tackles multicollinearity by regularizing the coefficients, not by removing features. It's a subtle but important difference. This refers to a type of regression that uses a Bayesian approach, incorporating prior information about the model parameters. This helps stabilize the model and reduce the impact of multicollinearity. This is ordinary least squares regression. It's very susceptible to problems caused by multicollinearity, where highly correlated features lead to unreliable coefficient estimates. Bayesian ridge regression uses regularization to handle multicollinearity. Regularization techniques, in this case implied by the Bayesian approach, constrain model complexity, reducing the impact of correlated features on the model's parameters. OLS regression is much more sensitive to multicollinearity. Small changes in the data can significantly alter its coefficient estimates because of the instability inherent in the method when features are correlated. I'll explain how Bayesian ridge regression handles multicollinearity, which is when multiple features in your data are highly correlated. It's a problem because it makes it hard to figure out which feature is truly important for your prediction. Bayesian ridge regression cleverly uses a Bayesian approach, incorporating prior information, what we already guess about the data. This prior information helps it stabilize its estimates, even with the messy, correlated data. It's like having a safety net. It prevents the model from getting overly swayed by any one correlated feature. We're using the Bayesian ridge model from the scikit-learn library, which is a popular tool for regression tasks in machine learning. We're training it on a dataset with correlated features, multicollinearity, and want to understand how it behaves. We are given 4 statements and asked to identify the correct ones regarding the model's behavior in this situation. This statement is correct. Bayesian ridge regression really shines when we have multicollinearity. It's a significant improvement over ordinary least squares, OLS, regression because the Bayesian prior helps stabilize estimates and reduce variance, reducing the impact of correlated features. Think of it like this. OLS is like a seesaw, easily unbalanced by correlated features. Bayesian ridge is more like a sturdy table, much more resistant to being knocked off balance. This statement is incorrect. While extreme multicollinearity can impact the predictive performance of Bayesian ridge regression, it won't necessarily be severely impacted. It's much more robust than OLS. The impact will be less than you'd see in OLS. This statement is incorrect. Bayesian ridge regression doesn't automatically detect and remove correlated features. It addresses multicollinearity through regularization, shrinking the coefficient estimates, not through feature selection. I'm going to explain how Bayesian ridge regression handles multicollinearity, a situation where your input features are highly correlated. This is a key concept for understanding how this model works differently than other regression methods like ordinary least squares. We'll see that Bayesian ridge regression offers advantages in handling this challenging situation. We're using a popular machine learning algorithm called Bayesian ridge regression, from the scikit-learn library, to make predictions. Imagine we have a dataset where some of our input features are highly correlated. That's multicollinearity. The question is, how does this affect Bayesian ridge regression's performance and the way it works? Specifically, I'm focusing on the scikit-learn library's Bayesian ridge function. This is a tool we use to build regression models. That is, models that predict a continuous value. We're interested in understanding how it behaves when our dataset has multicollinearity. This statement is true. I'll explain why. Bayesian ridge regression uses a Bayesian approach, adding prior knowledge to help guide the model's estimations. This prior information helps stabilize the model's parameters even when input features are strongly correlated. Ordinary least squares, OLS, regression lacks this stabilization, making it more prone to instability in the face of multicollinearity. This is FALSE. While severe multicollinearity can affect the predictive performance, the impact is usually not as severe as it would be in other methods like OLS. Bayesian ridge regression's inherent robustness makes it better able to handle such situations. This is FALSE. Bayesian ridge regression does not perform automatic feature selection. It doesn't actively remove correlated variables. Instead, it handles multicollinearity using regularization, a technique that helps to control the influence of each variable. This is the question that guides our analysis of the model's behavior in the presence of multicollinearity. The different answer choices test our understanding of how this model deals with correlated features. This title tells us that I'm going to learn about how the Bayesian ridge regression model handles multicollinearity, which is when multiple features in a dataset are highly correlated. This is a key concept in regression analysis. This is the core question. I am asked to think about how Bayesian ridge, a specific type of regression model, acts when dealing with data where some features are strongly related to each other, multicollinearity. It's a great challenge. This statement says that Bayesian ridge is better at handling highly correlated features compared to another common regression method, ordinary least squares, OLS. I need to determine if this is true. Bayesian Ridge uses a Bayesian approach that helps to stabilize results even when features are correlated, unlike OLS regression, which can become unstable in this scenario. Here I'm asked if the accuracy of my model's predictions will suffer greatly from multicollinearity when using Bayesian Ridge. It's important to understand that, while it's more robust than OLS, extreme cases of multicollinearity can still affect prediction, but not as severely as in OLS. I need to think about whether Bayesian Ridge automatically removes the problematic features. I should remember that it doesn't. It handles multicollinearity through its statistical approach, not by feature removal. This highlights the specific machine learning algorithm I'm using. I need to understand its key properties, especially how it manages multicollinearity, to answer the question correctly. It's an advanced technique that uses Bayesian statistics to improve the robustness of predictions. This question asks you to assess your understanding of how the Bayesian Ridge model in scikit-learn handles multicollinearity, a situation where some of the input features are highly correlated. I'll be focusing on the effects of multicollinearity on the model's coefficient estimates, the numbers that quantify the relationship between each input feature and the outcome, and its predictive power. This statement suggests that the Bayesian Ridge model will produce unreliable coefficient estimates when features are strongly correlated. That's incorrect. Bayesian Ridge is designed to be more robust to this issue than ordinary least squares, OLS, regression, which can result in unstable coefficient estimates in the face of multicollinearity. This is the correct answer. I'll explain why. The Bayesian approach in Bayesian Ridge uses prior information to regularize the model. This means that it shrinks the coefficient estimates toward zero. This helps stabilize the estimates and makes the model less sensitive to the fluctuations that multicollinearity introduces. OLS, on the other hand, is more susceptible to these fluctuations. Here, we're considering whether highly correlated features significantly reduce the accuracy of Bayesian Ridge's predictions. While some negative impact is possible, it's unlikely to be severe. Bayesian Ridge, with its regularization, handles multicollinearity better than OLS, meaning its predictive performance is less likely to suffer a dramatic drop. This statement wrongly attributes feature selection capabilities to Bayesian Ridge. Bayesian Ridge doesn't automatically identify and remove features. It addresses the problem of multicollinearity through its regularization techniques rather than feature elimination. This refers to the Bayesian Ridge regression model from scikit-learn. It's a type of linear regression model that incorporates a Bayesian approach to estimation, making it more robust to multicollinearity and overfitting compared to ordinary least squares regression, OLS. OLS stands for ordinary least squares. It's a common method for fitting a linear regression model. However, it's more sensitive to multicollinearity, and can produce unstable and unreliable coefficient estimates. In the context of Bayesian Ridge regression, this is information about the model parameters that is included before analyzing the data. It's like having an educated guess about what the coefficients might be before you even look at the numbers. This prior information acts as a regularizer. Regularization is a technique to prevent overfitting by adding a penalty to the model's complexity. Think of it as imposing a constraint on the coefficients, a way to keep them from getting too extreme. In Bayesian Ridge, the prior acts as a regularizer. This refers to the process where the regularization in Bayesian Ridge pulls the coefficient estimates toward zero. It's a way to reduce the impact of multicollinearity and to prevent overfitting. It's like putting a gentle brake on the coefficients. This describes coefficient estimates that are less sensitive to small changes in the data. The regularization provided by the Bayesian approach in Bayesian Ridge helps lead to more stable estimates compared to OLS. Especially when dealing with multicollinearity, the opposite of stable estimates. These are coefficients that change significantly with small changes in the data. This is a potential problem with OLS regression when multicollinearity is present.